Hello, good evening, everyone. Okay, so hi Lalit, hi Ashok, hi Vipul. All right, you can see there are 8 people here. Okay, right. So, before I start the session, as you all already know, this session is on database normalization. So, before I start the session, can I just have a quick raise of hands on how many of you know about the concept or have previously, gained some knowledge about the concept or some such? Hi Kishore, hello Abhinav, hello Ankit. Okay, anyone else? If you have a problem with the audio, could you please just, raise your hand or iterate the same thing so that I can just check for it? Hello Digvijay. Hi Ashwini. All right. No knowledge. What about the rest of you? I just asked a question, a simple question. Hello Kundan. So, yeah, how many of you have? Okay, there's a noise. Okay, just a minute. There is a noise. Just give me a minute there. Yeah, I think now the noise is a bit softer. If I could just have a confirmation of the same. All right. Fine then. So, without further ado, we'll just start off with the session. So, yes, as I've seen, some of you have some experience with databases. There are people here who would have already learnt about databases. There are people who will actually be coming for a database class for the first time. Now, the topic that we're going to tackle today is database normalization. Now, while we're looking at normalization, the first thing you need to remember is that even though the term seems big, all it means is that you are putting your database into a uniform of sorts, right? So it means that you are formatting your database in a certain way. How we're going to do that, what are the various ways to do that, why we do it, that is something that we'll be looking at in this particular course. And in between, I will also be taking up your questions as in when I'm completing, like between any two types of normalizations, I will be taking up your questions here. So if you have any questions, please keep putting them on the chat. Fine. So let's start with our session. So as I've already said, we'll be looking at the various types of normalizations that we have, and we'll be looking at what normalization actually is. So first of all things, why do we need normalization? We require normalization so that everything in our database can be put into a format. Now think about it as if you were in a school and you were in a uniform. Now when you're in a uniform, you will see that if there are any anomalies, especially in an assembly line, your teacher or head girl or your own class CR would be the first one to pick you or anyone who had something wrong with their uniform. So that is what uniformity does. It actually helps us in presenting all of the problems that possibly might be there in any kind of scenario. So that is what normalization does here too. So let us look at formally, let us look at why we require normalization. So the first thing is that it reduces the amount of repetitions of data that we might require. While we actually go through normalization, we'll see, just give me a minute there, guys, it seems that my voice is not clear. Okay, I can't seem to understand what the problem is. Um, if I could just have a very quick review of all right. Okay, so apart from the buzzing noise, is there any other problem that is there? Yes. All right. So we'll continue with the session. Let's see if it clears up on its own or some such. All right. Okay, now it's fine. All right, so I guess that has been cleared up. Very good, very well. Okay, so as we were saying, when we look at normalization, normalization helps reduce repetitions. Now, why are there repetitions? So I'll just give you a very short example of it. Say for example, you have two tables, right? You've got the student table and you've got the course table, right? So within the course table, suppose you have course name. I'll just be writing short forms here. We'll have course name. We'll have, say for example, course fees. We might have an HOD name given here, etc, etc, etc. On the other hand, you've got say student name here. We've got the course name again here, and let's say we've got the CR's name here within the student table, right? So this is just an example of two possible tables, right, in a class. Now, if these are two possible tables in a class, can you see that there are repetitions here of the course name? Now, what happens if you want to make a change in the course name? Ideally, you would have to go to each and every student who has, say, taken a particular course, and you'll have to go and change the course name everywhere, right? So actually doing that is not logical. It's not feasible, because even if while we're taking an example, we might have, say, 5 or 10 or 15 records or rows in our table, but when we are actually looking at a practical scenario, we'll have to add, say for example, 2 more zeros in each and every one of this place. So there are multiple records where we'll actually have to make those changes. So these repetitions or redundancies are actually not practical. So normalization helps us in removing those. Next, we've got modularization. Now, what modularization does and what it helps us with is actually two things. It helps us in isolating the entities. So when we isolate entities, it means we are separating one kind of entity from another kind of entity. Now, as soon as we do something like that, what it helps us with is it helps us reduce any kind of problems or anomalies or mismatches that might occur within our database. There are three basic anomalies that we'll be discussing further as we go ahead within the session. And lastly, when you modularize something, that is when you break something down from, pardon? Okay, seems to be that the problem is still there. All right. Okay. So, lastly, when you modularize or you break down any problem into smaller parts, it becomes easier to manage. Like if there is any issue with, say, one small table or one small record or one small value within that table, you know exactly where the problem is. So you can go there, resolve the issue. Say maybe if you have to delete the data, you might delete the data to resolve the issue. Whatever it is, you know exactly where the problem is. You can maintain that issue, you can mitigate the issue, you can carry out whatever mitigation steps are required there. So it makes the overall tables and the database also more manageable, right? So these were the advantages or the need for normalization. Next, we've got 5 basic types of normalization, and then we've got a variation on one of the types here. So the 5 basic types are the first normal form, the second normal form, third, fourth, and fifth normal form. Now, most of the time in most of our courses, we learn just these, right? The Boyce code normal form is actually the extended version of the third normal form. It's actually a stricter version of the third normal form. So we'll be looking at these actual 6 normal forms here. The first 3 normal form are extremely practically implementable. The fourth and fifth normal form are generally taken up only as theoretical subjects. And the reason behind that is because if you're taking care of the first, second, and third normal form, then you will actually understand that it resolves most of the issues that are there in the fourth and fifth normal form. But still, because it's a part of the normal form, we'll be doing all of these 6 normal forms here, right? Uh, Out of the box question. I can't see your question. I'm sorry, Shah Tariq. Any which ways, after this, after the first normal form, I'll be answering your questions if you have any. So we'll quickly go on to the first normal form here. So in the first normal form, let us look at the rules that are there for the first normal form. So thankfully for the first normal form, since it's the most basic normal form, we have just one rule: atomic values. Now, atomic values is something that, you get confused about. What are atomic values? Don't think about it. It's very simple. Atom. That's it. We had learned some time back, like when we were really, really little in like 6th or 7th standard, that atom was indivisible. Later on, we came to know it's wrong, but that was the first idea in our mind, right? That the atom is indivisible. You can't break atoms down. That is what atomic value actually is. Any value that can't be further broken down. So I'll give you an example. If you've got, say for example, a list of favorite foods, right? It's very rare to have only one favorite food. You might have ice cream, chocolate, pani puri, chaat, an n number of, maybe even infinite list, wherein those would be the numbers of your favorite foods. So all of that list can be broken down into smaller parts, right? So anything that can be broken down into smaller parts is known as non-atomic, and anything that can no longer be broken down is known as atomic. So let's look at an example to actually resolve all of that. Just look at this example given here, right? Can anyone tell me which of these 3 columns has non-atomic values in it? Yes, if you could quickly just answer here. Which of these columns have non-atomic values in them? Yes. So some of you have answered here. Yes, you're right. It's name. Yes. Why is it name? Because as you can see in name, we've got first, middle, and last name, right? Or in some cases, we've got first name and last name. Or in other cases, we might have first name and middle name. So this name column can actually be broken down into pieces. So this particular column is non-atomic in nature. So that means the table given here is actually not in the first normal form. If you look at numbers, these are atomic. This is a 10-digit mobile number. It can't be broken down, right? So currently the mobile number is atomic, and age, again, it's like one single value for a given person and you can't break down age, right? So yes, you're right. All of you are right here. We've got name, which is a composite value. That means it is made up of various parts. It is non-atomic in nature. So how do we actually resolve this? One of the simplest ways to resolve this is convert it into 3 different columns, right? So instead of having one name column, we are now going to have one column for first name, one column for middle name, and one column for last name. So that is how it will be arranged. We'll be writing, say for example, Jane here, Elizabeth here, and Fawn here, right? Similarly, since this is the first name and the middle name, it'll come here. What about last name? We'll leave it blank. right? Next, we've got, I won't write Harry James Potter here, it's too long. Let's see, we've got Ronald Weasley. Yeah, I am a huge Harry Potter fan, so you can see that from the names here. Anyways, so this is what we can do to any of the tables which have non-atomic values. Split them up on the basis of their components, right? So what does this actually help with? Now, when you look at this particular table, you have one value in each and every column, in each and every row. Now, what is the practical application of this? It seems like when you actually do this, it seems pretty useless. Why do we need to do this? The data meant the exact same whether it was in an atomic or a non-atomic manner. How did this actually help us? Let me give you an example. If your data is stored in this manner here, can you write a message on the screen of the form, hello, first name? Yes or no? If your data is in this form, wherein your first name, last name, and middle name are all together, can you write a message using the data in your database? Can you write a message on the screen stating hello, first name? Yes. Exactly. It becomes difficult to do that because how do you extract? How do you know which one is the first name, which one is the last name? That becomes a problem, right? So if you have messages, like many of you might be receiving messages on your phone at any given point of time, especially telemarketing messages stating, hi, so and so, hi, XYZ, you have a new offer. So the way in which they get your data is actually from a database that is formatted like this, where first name, middle name, and last name are all split up and then they're put here, right? So this was how actually we can convert any table which is in a non-atomic form into an atomic form. Just split the column into various columns such that in each and every row, in each and every column, you have just one value, right? Indivisible value. Chalo. Next, let's go on to the second normal form. PDF link in chat. Okay. All right. Mobile number is atomic. Yes. Age was atomic. Age was atomic. Name was non-atomic. Yes. All right. Fine. So let's look at second normal form since none of you have any questions here related to first, second, and third. So I will now start off with the second normal form here. So what is the second normal form? Now the second normal form is another kind of normal form which is at a higher level, right? So we have already seen in the first normal form that all of the values must be atomic in nature. Now what the second normal form tells us is that not only should the values be atomic in nature, right? So the first stipulation is that the table must already be in the first normal form. Now this is another way of writing first normal form 1NF. Similarly, second normal form can be written as 2NF. Right? So the first stipulation as stated here is that the table has to be in the first normal form. The second stipulation is that it should be fully functionally dependent. Now what should be fully functional dependent? The non-key attributes must be fully functionally dependent on the primary key attributes. Now most of you here know what the primary key attribute is, right? Now the primary key attribute is an attribute or a column name, right, which can uniquely identify any of the record in that particular table. So if you look at the student table, one of the easiest way to explain student table on the basis of primary key is your student roll number. So if any given class has a table created, right, of the number of students that are there in the class, you will find that each student's name will be written right beside their roll numbers. That is because roll number is easily able to identify the names of all of the students in the class. So those are your primary keys. Any of the keys that uniquely identify each and every record, that is a part of the table. Now what your second normal form is saying is that each and every one of your non-key attributes, all of those attributes that are not the primary key attribute, have to be fully functionally dependent on the primary key attribute. Now what does this functional dependency mean? And what does fully functionally dependent mean? So in order to understand that, first let us look at functional dependency, and next we'll look at full and partial functional dependency. So these are the three concepts we'll be looking at here. First, if we look at full functional dependency, we've got a concept wherein any kind of attribute which is non-key attribute, so something which is not a primary key, it can't uniquely identify itself, this particular non-key attribute would actually be dependent upon a key attribute. Now, many of you would have realized here that I wrote it in the opposite manner. It's because there are two ways to actually say this. We can say X defines Y. This means that X is the primary key and Y is the non-primary key that is being defined by X. And the other way to say this is that Y is functionally dependent upon X. So it's the exact same thing. You have Y, which is a non-key attribute. You've got X, which is the key attribute, and X is the one that is able to uniquely identify Y, right? So this is how we denote it. Now that we've understood functional dependency, again my voice got tempered. Okay. Yeah. So now that we've understood functional dependency, let us see what full and partial functional dependency is. So in order to understand full and partial functional dependency, we'll have to understand what composite keys are. So if you look at any kind of composite key where you've got, say for example, two keys. Let's take student ID and student email. Okay. So these are two logical keys that are actually going to uniquely identify each and every record. Now, if you look at full dependency, in full dependency, if I name this D, for example, in full dependency, I would have a non-key attribute, say for example, student name, which is going to be fully functionally dependent on this D, right? If I take out only SID, it should not be functionally dependent. Now in this example it is, just bear with me for a minute, or let me see, I'll give you another example if that will help. Okay, so let me just change the example here. Say okay, so I've changed the composite key here to roll number and class number. So imagine roll number is just like 15 or so and class number is 12A, right? So if I talk about a student being roll number 15 in 12A, I am able to uniquely identify that this particular student is one of them, right? Let me take just roll number 15 as an example. If I'm taking just roll number 15, will I be able to uniquely identify any student? No, right? Because roll number 15 could exist in, say, for example, 12A. They could exist in 12B. They could exist in 12C. They could exist in all of the 12th classes. Not only that, they could exist in the lower classes also, right? On the other hand, if I'm looking at 12A only as the class number, will I be able to uniquely identify a student? No, obviously not. And why is that? Because there could be two students who have the same name. Like most of us have seen people having the same name, right, in a class. So for example, you might have 3 Nehas in the class. You might have 4 Amits in the class, right? So just the class name is not going to uniquely identify the record, neither is just the role name going to be uniquely able to identify the record. So in this case, where the parts of your composite key are not able to uniquely identify your records, it's known as full functional dependencies. This means that the whole identifying element has to be taken up, and the non-key attributes is fully functionally dependent upon that whole attribute and not dependent upon any part of it, right? But if any part of D is taken up, say for example, X is a part of D, and we've got an attribute Y such that even though X is a part of D, Y is able to completely depend upon this part of D, then it will be known as partial dependency. Right? Just give me a minute here. Yes. Okay. So what does our stipulation here say? It says that our non-key attribute must only be dependent upon the primary key attribute, right? Only be dependent and fully functionally be dependent upon whatever primary key attribute we have chosen here. Let's look at a quick example for this. Yes, so this is the example. Now, if you see here, this is a student table, right? In this student table, logically, our student ID would be the primary key, right? So let's look at the first column here. We've got first name. Yes, first name is obviously dependent upon the student ID. Let's look at age. Let's look at project ID. Let's look at project name. We have all of these columns here. When you observe them carefully, you will find that age and name actually fully functionally depend on student ID. So this is the student ID, this is the student ID's name, and this is the age of this particular student. That is perfect. But are you able to form the same kind of relation between project ID and project name? Sorry, I'm so sorry about that. Okay, yeah. Are you able to make the same decisions about project ID and project name? No, right? If you look closely, actually, you'll find that the project name is dependent upon the project ID, and the project ID is currently not dependent on anyone. Until and unless we don't say that this particular student is actually taking up this particular project, till that kind of a relation is not here in the picture, we can't really say that the project ID or the project name is related to the student ID in any way or form, or is dependent upon the student ID in any way or form, right? So here we can see that these two columns are actually not dependent upon the primary key. Okay, I can see a question here. What is non-key attribute? Non-key attributes are all of those attributes that are not primary keys or unique keys or super keys in nature. These are concepts that we might be doing in another session or so, or you might have already done in a previous session. If not, just put a comment right in the live chat, and we'll see if we can take up those sessions too. Any key that can't uniquely identify itself or can't uniquely identify any others are known as non-key attributes, right? So what do we do here in this case where we've got these attributes which are not dependent upon the primary key? Very simple, just convert them. All right, split the table and convert that one table into its components. All right, now here it is actually fortunate that we've got the student ID column. Many a times there would be no student ID column, there would only be project name, right? So here what have we done? We've split up this initial table into a new student table and a new project table. Now when you look at these two separate tables, you'll see that this non-key attribute is dependent upon the key attribute. Similarly, this non-key attribute is dependent upon the primary key attribute. And the same thing can be noticed here. Project name, which can't really uniquely identify itself, is now dependent upon a key which is able to uniquely identify the project name. Apart from that, in each and every place you can see that if we are talking about a non-key attribute, that means an attribute that can't identify itself, if we're talking about that kind of an attribute, then it is fully functionally dependent upon the key attribute or the primary key attribute, because there is no way that you can split up the primary key into bits and pieces, right? So if there is a value here, it has to be dependent upon the primary key only for unique identification. So this is how we actually convert from non-second form table into second normal form table. All right. Anyone having any tables? Yes, actually, MMIT Academy has stated the right answer, your separate columns. I missed out on that as I was presenting here. All right. Okay. So anyone having any doubts regarding the second normal form? If not, we can quickly shift to the third normal form given here. Sorry about that. All right. Okay. So one thing I would like to tell all of you is that maybe my voice might crack in between, and that is majorly because of my own throat rather than any problem with the system here. So please bear with that. Yes. All right. Okay. So let's go on to, since no one has any doubts here. Yes. Yes. As far as I can see, there are no doubts here. Okay, so let's go on to the next topic, which is the third normal form. So, what is the third normal form? Now, if I go on to the third normal form, there is a pattern that you will see, right? In the second normal form, we had a stipulation that the value has to be, already existent in the first normal form. Now that we've come on to the third normal form, we have a stipulation here that the value has to already be in the second normal form. So there is a sort of cascade that goes on here. Every new normal form will stipulate that you have to be in the previous normal form, and then I can carry you forward, right? So it's almost like you going on to a new standard or a new class, right? You have to pass this particular previous class, and then there are additional stipulations which will allow you to pass the next class, right? So it's the same thing even in normal form. Now here, apart from having the stipulation of the table already being in second normal form, so that means first of all things, all of the values in the tables must be atomic in nature. And the second concept here, or the second stipulation here, would be that all the non-key attributes should be fully functionally dependent upon the key attributes. So this is what second NF tells you. Now, apart from this, there is also another stipulation here that there are no transitive dependencies. Now, what are non-transitive, or what are these transitive dependencies, so that we can understand what not having this means? Now, transitive dependencies are like law of transitivity. So what does law of transitivity say? If we have A equal to B and B equal to C, then A equals to C. Yeah, I know. I said it in a sing-song manner because that is exactly how we've learned it, right? So if we have a connectivity between any two objects, and the second object has a connectivity with the first object, I'm sorry about that, yeah, then it will obviously follow that the first object has a connectivity to the third object, right? This is transitivity. So even in functional dependencies, we've got that type of a transitivity. If A defines B and B defines C, then it stands to reason that A defines C. This is transitive functional dependency. You can also read this in the opposite direction. That means if B is functionally dependent on A and C is functionally dependent on B, then C is functionally dependent upon A. So this is what transitive dependency is, and this is something that should not exist in our third normal form. So what do we do if it exists, right? Answer is very simple. You split up the table logically. Now, everywhere that we look at for normal forms, one thing that you'll find in common is that the solution, apart from for the first normal form, is splitting, right? If you ask me why are they constantly splitting it, the answer is very obvious. It is to make it more modular, right? The more modular you make, the smaller pieces you break it up into, the more isolated all of these pieces will get. The more isolated they are, the less problems that they'll have in between them. So that is what we're trying to do here. We're trying to split a relation into various separate parts so that even if they interact with each other, they're interacting with each other without any issues, right? So let's just look at an example of the third normal form. Now, apart from looking at an example of the third normal form, I'm also going to discuss some anomalies here. Right now, as I had stated previously, there are some anomalies that will be there in the database. Now, let's look at the most basic anomalies that we have here. Just observe this table. First, let us look at what anomalies exist here. So we've got three different anomalies. We've got the insert anomaly, we've got the update anomaly, and we've got the last anomaly, which is the delete anomaly. Right? Now, what are these three anomalies? Think about it for a minute here. Right? So we've got this particular table, and this table is such that we've got student ID, and this course here can be stated as being dependent upon the student ID, and the course fees is such that it is dependent upon the course, right? So we've got 1A, which is defining a B attribute. We've got B attribute, which is defining the C attribute. But think about it logically. Should A be defining C? Should your student ID be defining the fees? No, right? That does not make sense, because that will mean that based upon who the student is, what the student is, how the student is, you will be able to change the fees. But that shouldn't happen, right? The fees should be the same if the student is in the same course. As per A defining C here, what it means here is that for John, since John is S02, I can change the fee to, say, for example, 35,000. And because I like S03 as a student, I might reduce their fee to 25,000. Why is that? Because I've said that, yeah, there is transitivity here. A can define C. So C's value can also be changed based upon A, right? That should not really happen here. Right? So this is why transitivity is actually bad. Transitive full dependencies are bad because of this reason. They actually give rise to illogical concepts being rationalized, right? Next, let's just look at the anomalies. For the anomalies, what I'm going to do is I'm going to change the color here so that it's more clearly visible. Just look at this anomaly here. So the first anomaly I'm going to discuss is, say, for example, the delete anomaly. Okay, just observe this particular row here. We've got due to mic problem. Okay, that is an issue now. Okay. Let me do something. Just 1 minute. Yeah. All right. I hope, fingers crossed, that this has resolved the issue. So I'll continue forward with the session. Just look at the row given here, which is S06. Okay, S06 is a student called Hermione. Again, as you know, Harry Potter fan here. So this particular student is a student who has taken admission in BMS, and the fees of this particular student is 40,000, right? And the age of the student is 20. Now, what happens if, for whatever reason, Hermione says, okay, I don't like University X, I'm going to University Y, and she retracts her admission. She leaves the college, right? So this particular row will no longer be a part of this particular table. We'll have to delete this row altogether, delete it, right? So if we're deleting this row, what are the only courses that will be left in our table? We'll only have IT and CS. Does that mean that BMS is no longer being offered by the university? Right? That's something to think about, right? Just because a student retracted their admission from a given course, we are losing the details of that whole course. Should that be the case? No, right? That is why it's known as deletion anomaly. You're deleting something and it's causing another problem altogether, right?
Let me just clear up the slide a bit so that it's easier to see the rest of the data. It's become a bit too congested here. Okay, a minute there. All right, yes. Next, let's look at the other anomaly, which is update. All right, so say for example, I want to update the fees of the course IT to 38,000, right? Now, what will this table do? Or on firing this particular update query, what would happen here? We would go to this particular IT course, go to this particular fee, change it to 38,000, right? We would find the next IT, some selection projection operations will be taken care of. Here this will cancel out, you have 38,000, right? These were 5 records. From these 5 records, 20 of these records were changed. I'm sorry, 2 of the records were changed. Imagine if you have 5,000 records and 2,000 records have to be changed in a similar manner. Now, even these values are on the lower side, right? You might ideally be having 50,000 records from which 20,000 records have to be changed. Just imagine how much time it would take to actually go and update each and every record containing the IT course and update its value or its course fees value to 38,000. It's a waste of time. It's a waste of processing time. It's a waste of processing throughput, right? So this is what the update anomaly is. Unnecessarily, you have to go and update various elements that are a part of the table because the table has not been created properly, right? Lastly, let us look at insertion. What is insertion anomaly? Insertion anomaly is actually the flip side of deletion anomaly. You can't insert a course here till a student does not opt for it. So for example, say the college or the university that this particular table belongs to has a BMM course, right? Bachelor's of Mass Media course. But that course can't be seen anywhere here. And the reason for that is very simple because currently there are no students on the record who have opted for this particular course. So even though the college is offering course, even though the data exists within the environment, it is not reflected within the entity. So these are the 3 types of anomalies that are often seen up till the third normal form, right? Let us look at how we can resolve this. So if we look at this carefully, resolving this is actually oh, that's bad. Yes, now it's good. So resolving this is a simple matter of, again, splitting up the table. Now, how are you splitting up the table? We know for a fact that, I'll just quickly change the color here so that it's more visible. Yes. So we already know for a fact that the course and the fees were related to each other, right? Or I should say logically they should be related to each other. So we keep them related to each other and the rest of the values are related to or related within themselves. So first name and age would be related to student ID. Yes, that's proper. Course and fees should be related to each other. Keeping this logical division in mind, what we've done is we've put them into 2 separate entities or 2 separate tables. So we've got the student table and the course table. Now previously in the previous example, we had a project ID, right? Yes, we had a project ID. Here we did not have a course ID. So what we did, we introduced a new column for course ID. So now what is happening? We've got both of these tables in such a manner that they are all atomic in nature, right? First thing. Secondly, all of them have their own primary keys here. So both the entities have their own primary keys and the non-primary keys or the non-key attributes are dependent upon this primary keys for uniquely identifying themselves. And lastly, there is no transitivity here. Can you see that? This is uniquely identified by this. Similarly, age is uniquely identified by student ID. Course name is uniquely identified by course ID. Fees is uniquely identified by course ID. So now there is no dependency of the non-key attribute on another non-key attribute. You have a dependency on the course ID. So if course ID once fees is changed in this particular place, it can be changed everywhere else, right? So here we've seen how transitivity can be removed. Next, let us look at what about our anomalies. Have they been resolved? Yes, even the anomalies have been resolved. Let's look at the first anomaly. Say for example, update anomaly, right? As per the update anomaly, previously we had to go and manually change. The database had to actually go and change each and every record's fee. Here what happens? If you are updating the record here and changing the fee to 38,000, you have to do it only once. Wherever this particular record is related, right? Wherever these particular records are related, in all of those places, these changes will be reflected on their own, because the data has been changed in one particular place, right? So that is how the update anomaly got resolved. Next, let's look at, say for example, delete anomaly, right? So within the delete anomaly, what we saw initially was the fact that when Hermione removed her, or when Hermione retracted her admission, all of the records for BMS were lost. What happens now? Hermione retracts her admission, as was her wish, but the course details remain as they are, because now the course is no longer related so closely to the students that on deletion of the student, the course would also be deleted. That is not possible anymore. So our deletion anomaly, wherein our course data was also getting lost, or meaningful data was getting lost just because of deletion of a record, that has also been resolved right now, right? Next, let's look at insertion anomaly. Now, what was our problem with insertion anomaly? In insertion anomaly, we said that even if there is a course for BMM, we could not show it in this particular table because none of the students had opted for it. Here what happens? Irrespective of whether a student has opted for the course or not, we can attach the course to our table given here, right? Say it's got a similar fee of 40,000. So we can attach the course to the table here and preserve it in our database. Irrespective of whether a student is opting for it or not, the college is offering the course, the university is offering the course, so it is a part of our course table, right? So in this way, we have eliminated both the transitive dependencies, and we've also eliminated the related anomalies that we've seen, right? That is the insertion anomaly, the updation anomaly, and the deletion anomaly. Okay, could you please start first onwards? Okay, so what you can do, Afzal, is you can go back and watch the whole video from the start. Also, at the end of the session, what I'll be doing is I'll just be taking a quick summary of everything. So the summary as well as the rest of the video will actually help you understand the whole concept. If not, you can put your queries on the chat, right? Okay, any other questions here? All right. All right. No other questions here. Okay. So I'll continue forward with the stricter version. Okay. Now, the reason I said stricter version in this dramatic manner is actually very simple. It's because most of the people who are familiar with normalization are, for some reason or the other, scared of Boyce code normal form. Now, one of the reasons, and this is something that I've personally experienced, is because Boyce code normal form is shown as something which is very separate or very different, or is a newer, or I don't know, more specialized version of normalization. It's none of those things. It's actually a combination of the previously seen normalization. If you look here carefully, the first stipulation is very simple. Your normalization, or the table that you're trying to normalize, has to be in third normal form. As I've said, it's going to be cascading, so this is something which is very acceptable to us, right? And if you look at the second stipulation, this looks a lot like our second normal form stipulation, right? Non-key attributes must be fully functionally dependent on. The only change here is that they've spoken about super key here, right? So the second normal form says that the non-key attributes must be fully functionally dependent upon the primary key. And here Boyce code normal form says that your non-key attributes must be fully functionally dependent upon the super key. Now, the only concept we need to understand here is what is super key. So super key is like the superset or the parent set, or I would call it, say, the universal set of each and every key attribute. So from the superset or the super key set, you might have a subset which is the primary key, you might have a subset which is the candidate key, you might have a subset of composite key, right, of unique key. So all of these different kinds of constraints are actually subsets of the super key. The super key is the one that contains all of this, right? So what our Boyce code normal form is saying is that all the non-key attributes must be completely dependent upon the super key. Now, when is this possible? This is possible if and only if, I'm saying this because it's very necessary that you understand this very, very clearly. The most simplest manner, I know I'm using double superlatives, but the simplest manner to understand or to implement Boyce code normal form is to ensure that the super key consists of the primary key. All right. If the super key consists of the primary key and only the primary key, then Boyce code normal form becomes the simplest thing on earth, right? And by the time you come to the third normal form, I guess it becomes very difficult to have anything other than the super key, other than the primary key within the super key. But if in case you still have some other value as a part of your super key, please make sure that you're distributing or splitting up your tables in such a manner that you actually end up only exclusively with the primary key within the super key. All right, this will actually simplify your concept when you're practically implementing it. Let's just look at a quick example for Boyce code normal form. So here you have this table where you've got the student ID, the first name, the subject, the professor, and the age. Now, if you look here, this particular column does not really make sense, nor does this column make sense. Now, why am I saying that these columns don't make sense? Because a professor could be, a professor is not really related logically to be put up with a student, right? Similarly, a subject is not related logically to a student. Think about it in this manner. Here, for this particular example, we've taken one student having one first name, having one subject, having one professor, and having a particular age. But ideally, there would be a set of students or a bunch of students who are taking up the subject C++ and who are studying under Chetan sir, right? So if you're a bunch of students who are taking up, say, Java, for example, and studying under Javed sir or Jaya ma'am or Divya ma'am or Tara, and these are just fictional names, huh? No resemblance to any person dead or alive, disclaimer. So here, if you've got all of these various kinds of people, right, what you would ideally think about is the professor and the subject are related to each other, right? So professor is dependent upon subject and professor is not dependent upon the actual super key here, which consists of the primary key, right? So because professor is not fully functionally dependent upon the super key and subject is also not fully functionally dependent upon the primary key or super key in this case, that is why this particular example is not in Boyce code normal form. So changing that again, very simple, convert it into two different tables, and in both of these tables you logically split everyone up such that your first name is fully functionally dependent upon the primary key, age is fully functionally dependent upon the primary key. Professor's name and subjects were two values or two attributes that were related to one another, but there was no primary key between them. So we introduced a primary key professor ID here. Now what is happening? This particular professor is uniquely identifying, I'm sorry, I'll just repeat that quickly. This particular professor ID is uniquely identifying the professor and is uniquely identifying the subject too. This can further be split up. All right, I'm not saying this is the only way to do it. If you think about it logically, while you're creating your database, subject could be put up in a completely different table, right? But for this example, this is enough to convert a non-Boyce code table into two Boyce code tables, right? So this is how we perform this normalization in SQL practically. Samir, I actually do not have enough time here right now for practical performance of this. I will surely schedule that in another live session. All right. So please make sure that you are actually attending that live session too. Again, I would iterate till Boyce code normal form is where all of your implementations can be practically implemented. If this is done, your fourth and fifth normal form becomes extremely very simple. So the fourth and fifth normal form, as I've already stated, is mostly theoretical in nature. Let us just quickly look at what they are. So for the fourth normal form, the first component or the first stipulation is that everything should be in Boyce code normal form. Again, expected, right? Next stipulation is that all of your functional dependencies must be single valued functional dependencies, or as what is stated here, none of the multi-valued dependencies must exist. Now, what is this multi-valued dependency? Multi-valued dependency is actually as explained here. You've got one attribute such that it is defining another attribute, B. You've got the exact same attribute defining or uniquely identifying an attribute C, but these two attributes are in no way or form related to each other. So what is happening is that one particular column is uniquely identifying two attributes which have no commonalities between them, right? Now, here many of you might have a doubt, and these doubts will be cleared in just a minute. So just give me 1 minute to explain this. All right. Yes. Okay. So as you can see here, we have a table. So till now we were having tables which were very simple looking, right? We at least had a student ID, we had a first name, and we had age, right? So let's just compare these two types of tables wherein we have this which is not in fourth normal form and this which would ideally be at least close to the fourth normal form, and why there is a difference between the two. So let's just look at the example given here. I'll change the color so that it's better to see and simpler to understand. If we look at this example, which is completely not in fourth normal form, we'll see that professor, the attribute professor, is able to be uniquely identified by, I'm so sorry about that, yeah, is able to be uniquely identified by the student ID, right? On the other hand, textbook is also uniquely identified by student ID because these textbooks are, say, for example, being referred to by these particular students and these professors are teaching these students. So there is a relation between professor and student, and there is a relation between textbook and student. What about professor and textbook? Some of you might say that, professor has assigned the textbook, right? Not necessarily. Your curriculum could have stipulated that this is the textbook that you're supposed to use, right? Or your college guidelines would have stipulated that these particular textbooks are the ones that we have in our library, so you have to use this. So it's not necessary here that the professor is the one who's defining that this particular textbook has to be assigned. The student is getting assigned the textbook, yes. The professor is teaching the student, yes. But there is literally no relation between professor and textbook. So as we can see here, A, which is a student ID, defines B, which is professor, and A, which is student ID, defines C, which is textbook, but B and C have literally no relation in either direction to each other, right? So this is something that is not in the fourth normal form. Now, why have I given this example here? Because this example is not uh, a multi-valued dependency. That is because first name does uniquely identify student ID, and age also is uniquely identified by student ID, but there is a relation between a student's first name and their age. They both belong to the student, right? So logically there is a relation between first name and age. So this is not known as multi-valued dependency, whereas this is known as multi-valued dependency. So again, the simplest way to remove this multi-valued dependency is to actually split the table up. And we are splitting the table up in such a manner that all of the columns that are logically related to each other will be put up in one place, and all of the columns that are logically not related to each other will be split between the tables here. So what we've done, uh, yeah, so what we've done here is that student has been clubbed with professor, and again student has been clubbed with textbook. Why has this been done? Because we said that student is able to define textbooks and student is able to define professors. But since professors and textbooks have no relation with each other, they've been split up into two separate columns. Some of you might have a doubt. uh, what if we had student ID, first name, age, professor, and textbooks? Simple. Wherever you've got two things not related to each other, split them up. So we would get one entity with student ID, first name, age, and professor, and another entity with student ID, first name, age, and textbooks. Because these are related to one another, and then that is related to professors, and these are again related to one another, and then they are also related to textbooks. It's just professor and textbooks that have to be split apart since they are not related to each other, right? So this is how you can convert any kind of table which is not in the fourth normal form into a table which is a fourth normal form. The last type, let me just quickly look at the chat here. Okay, again we've got no doubts. uh, okay, this is scary because this either means that I'm a very good teacher, which I know is not really possible at the moment, or that you all are understanding everything, or you've got some other doubts, right? So, whatever your doubts are, as one student has already put up their doubt, can we perform this normalization practically? So, yes, I will try to hold another session wherein we will practically implement this particular normalization, at least 1, 2, 3, and Boyce code normal form. Um, if anyone else has any other doubts like these, you can just put them up in the chat below. I'm actually encouraging you to put them up in the chat below. Please do, because that will give me an idea of, whether you're understanding, whether you're not, whether you're able to, grasp the concepts or not. So please do put all of your doubts, all of your opinions, and all of that into the chat here. All right. Uh, since I can't see any doubts here, what I'll be doing is I'll just quickly go on to the last type of normal form, which is the fifth normal form. Now, the fifth normal form often becomes slightly confusing. It's because there are two conflicting concepts that are here. They're conflicting concepts because the concept looks like it is something desirable, but for fifth normal form, the concept is not a desirable concept. The simplest way to explain fifth normal form is you are trying to create an atomic table. Okay, so I'll just simply explain this a bit more. What we're trying to do in the fifth normal form is that we are trying to create a table, or we are trying to achieve the possible creation of a table which in and of itself, if divided into components, will lose meaning in its data, right? So one table that can no longer be divided further, that is what we're trying to achieve here. Just make a point of this. We are trying to achieve an atomic table. Please note, I'm not talking about one single value. I'm saying that the table is such that if you break it down, the table will lose meaning. All right. Now, in order to understand how that is done, let's just quickly look at the rules. First, as expected, the table must be in the fourth normal form. Next, there should be no join dependencies. right? Please make a note of this. There should be no join dependencies. We look at what join dependency is so that we understand what not having join dependency mean. And lastly, any and all joins that we make with this particular table, which is in fifth normal form, have to be lossless in nature. So there are two concepts we need to understand here. What is join dependency? And next, what is lossless? Okay, so first let's understand what join dependency is. If we take any table and we call it a relation because this is after all a relational database concept, right? So any table can be called a relation. If this particular relation is split up into multiple smaller relations such that they go from R1 to R2 to R3 on and on and on till Rn, actually performing a join operation between any number of these relations should give us back the original relation. We'll see an example of this, right? So don't get worried too much. We'll see an example of this to understand exactly what joint dependency is also. So what it is saying is basically if you're taking a join of R1 and R2 and R3 for that matter, you're taking a complete join of this. Then after taking the join, the relation that you'll get or the final result that you'll get will be the original table. That is what joint dependency is. What fifth normal form says is there should be no joint dependency. That means this should not be possible. After splitting up a table, if forming the join is giving you back the original table, then that particular table is not in fifth normal form, right? Next, what is the meaning of lossless join? In order to understand lossless join, we need to understand what is lossy, right? Because not having lossy will be lossless. So loss in any data can occur in two cases. In the first case, if you lose some data, this is obvious, right? You're losing some data. There is some data which was initially there and now it's not there any longer. So this is a loss. But another way, oh, I'll just quickly change this to actually denote lossy, because we are first going to understand what lossy is and then not this will be lossless, right? So losing some data is going to be lossy, and apart from that, having extra data is also going to be lossy. Why is having extra data lossy? Extra data is good. Extra anything is good, right? Extra chocolates are good. Extra mithai is good. If you like chaats, one more pani puri is also good, right? But here it's a problem. The reason is very simple. I'm so sorry about that. Um, the reason is very simple here actually. Loss of data is you losing out on data, but adding extra data is also a form of loss. You are losing out on meaningful data, right? Whatever meaningful data you had, you have lost out on it. You are now gaining extra data which is not meaningful in nature, and that is causing the actual loss of data. So if this kind of loss is not there in your database on joining something with the existing fifth normal form table, then that particular join is known as a lossless join. So what is join dependency? We've seen that. What is lossy decomposition? We've seen. And now we know that these two concepts should not be there in our fifth normal form, right? Let us just look at this with an example. So first I'm going to show you an example where there is join dependency, because of which this is not in the fifth normal form. Next I'm going to show you a table which is not having join dependency and can potentially be in the fifth normal form, right? Also, why did I just say potentially be? I'll be explaining that also later on. We have, I think, got around 5 to 10 minutes left, so I'll quickly go through this topic and the summary. So, first of all things, look at this particular component here. Now, the professor is teaching a particular subject. The student is given here who is interacting with the professor. All of the records here have no multi-value dependencies, so we can say that this particular table is in the fourth normal form. Now let us split up this table. Alright, so let's say that this particular table is relation R, and we are splitting this table up into three separate relations, R1, R2 and R3. Please make a note of this. This is just a splitting up of the table. There is the only logic I've utilized here is that I am forming some combination and permutation of all of the attributes that are given here, and I form three separate relations. There is no logic exactly to this particular splitting. It's just that the records existed, I have split them up. Try to perform a join on any of the two relations that are given here, say relation 1 and relation 3. So let's take relation 1 and relation 3. If I select this particular record here, so student S2 is actually learning with Professor Javed, right? This is as per relation R1. Similarly, student S2 is learning Java. What am I getting as the end result of this particular join? I'm getting that student S2 is learning with Professor Javed, and the subject that the student is learning is Java, right? This exact same relation or tuple actually exists in the original relation, right? You can actually do this for each and every one of the records that is given in R1 and R3. All of the records will give you back the records that are already part of relation R, which is the original relation. Take another set, right? Let's take, say, for example, R2 and R3, let them be in a join, right? So if we take R2 and R3 in a join, let's take this record right here. We've got Professor Divya who's teaching DS, and DS is being taught to student S4, right? So what I'm getting in the end is that student S4 is with Professor Divya, and that this particular subject being taught is data structures. When we look at our original relation, we have this particular record as it is. Again, if you go through all of the records of R2 and R3 in a join, you will find that all of the records will be reproduced as they were in the original relation. So by now you've understood that irrespective of whether you're taking R1 or you're taking R2 or you're taking R3 or you're taking all three of these relations, creating a join between them is going to give you some data that already exists in the original table. So we have join dependency here because the various parts of the relation or the various sub-relations, when they are in a join with each other, they are giving us back the original relation. Because this is in a join dependency, this can't be in fifth normal form, right? I hope you've understood why this particular example is not in fifth normal form. Okay, next let us look at this particular example here. Now this particular example, as we'll see later on, is definitely not in joint dependency, but we can't really say whether it is in fifth normal form or not, basically because there would be some anomalies here, as we'll see later on. All right, so sorry, I'm very sorry about that. So let's look at how we've split this. So let this be our relation R, and in this relation R, let us split it up into R1, R2 and R3. Again, we've done the same thing. We've just taken up our relations, just split them up, taken two columns for each and every relation here. Now let us try to create a join. Say for example, we're creating a join for relation R1 and relation R2, right? So we've created a join for relation R1 and relation R2. What is going on here in this join? Say for example, we are looking at student S1. Student S1 is under the tutelage of Professor Chetan, and Professor Chetan is teaching subject C++. We are perfectly fine here because this particular record is as it is in our table here, right, in our original relation R here. Next, what happens if we take the second one? We've got student S2 here. Student S2 is with Professor Javed, and Professor Javed is taking Java. So yes, student S2 is with Professor Javed and Professor Javed is taking Java. But Professor Javed is also taking DS. So for the student S02, we're getting Professor Javed with Java, and we're also getting for the exact same student Professor Javed with DS. Now there's no problem with this particular record here because this exists here. So we do have joint dependency there. But can you see this record? This record does not exist anywhere in the original relation. So actually performing a join between R1 and R2 is not giving us back the original relation. This means that there is no joint dependency in the original relation. If there is no joint dependency in the original relation, I can say that this particular table has the potential to be in fifth normal form. The reason I can't exactly say whether or not this is in fifth normal form or not is because I've not checked any joints between this relation R and another relation R2. So remember, there are actually three stipulations. First, the table should be in fourth normal form. Second, the table should not be a joint dependency. And thirdly, that any of the joints that are performed with this particular table should be lossless in nature. Because I've not checked any joints of this table with another table, that is why I still can't say whether this is in fifth normal form or not. Because based upon whether that particular relation is going to be lossy or lossless, then I will be able to determine that. So what we've understood here is just whether this table has joint dependency or not. Since it does not have joint dependency, it has the potential to be converted into fifth normal form, or it has the potential to be in fifth normal form, right? Any doubts regarding fifth normal form or so? If not, or even for that matter, first to fourth normal form, if anyone has any doubts regarding any of the normal forms, you can put them quickly on the chat given here and I'll quickly just go through them. If not, let's go to the summary. All right. So no doubts here. Can I get recording video, Rohit? Mostly as far as I know, this particular video will be there on YouTube, I guess. So also you can just go back and watch the whole video again. So yeah, I guess this should be helpful. Also, if at any point of time you have any doubts, you can put them up on the chat. Okay. All right, so as there are no more doubts here, what I'll do is very simple. I'll go on to the summary. So what have we studied in this whole session? So this is the end of the session, right? There are two things that I actually want to tell you. We'll be going through the summary quickly and then I'll just point out a few points that we need to remember, right? I'm just putting this here so that I remember that I need to go through this, and let us quickly go through the summary now. So the first thing we've looked at is what was normalization. When we were going through normalization, we saw exactly what it was. So we said that it was a way in which we could uniformize the format that is there in the database. We also saw why we required normalization. So the why was very simple. Firstly, in order to actually identify any kind of anomalies that we had within the system, we were able to actually isolate the various elements from each other. We were also able to better manage and reduce redundancy within our database tables. Next, we saw what the first normal form was. So in the first normal form, we had only one stipulation that all of our values have to be atomic in nature. That means they should not be able to be divided any longer, right? Next, we saw what 2NF was. So 2NF had two stipulations. One was that the table had to be in the 1NF state, and secondly, that all of the non-key attributes had to be fully functionally dependent upon the primary key. Next, we saw the third normal form, wherein the stipulation was that all of the tables that are actually being considered for third normal form have to be in second normal form, and that there should be no transitive functional dependency. I'll just write this quickly. Yes, transitive functional dependencies should not be there. Next, we had our Boyce code normal form. In Boyce code normal form, which is a stricter form of our 3NF, we had a stipulation that everything should initially be in 3NF, and then we said that all the non-key attributes have to be fully functionally dependent upon the super key, right? Next, we had 4NF, where everything had to be in Boyce code normal form, and there should be no multi-valued dependencies. And as we saw, multi-valued dependencies are when we have one attribute defining another one, we have the same attribute defining a third one, but the defined attributes, the dependent attributes, are not related to each other. That is when you get multi-value dependencies, and we had to eliminate those. Lastly, we saw 5NF, which is the fifth normal form. We saw that in fifth normal form, we actually had to have all of our tables in the fourth normal form. And next, we should have no join dependencies, and any joins that we create with the original relation have to be lossless, right? So first of all things, the original relation should not be able to be split into various other relations. And if you try to do that and then try to join the relation, we should not be able to get back the original relation. That is what no join dependency means. Next, if you actually take up the original relation and perform a join with some other table or some other relation, that join should be lossless in nature. So these were the stipulations. Now let us go on to the points that I wanted you to remember. Point number 1, always make tables which are logically making sense, right? So all the student data will go in the student table, or the course data will go in the course data table, all department data will go into the department table, right? Make sure, second of all, that you've got primary key and foreign key constraints used anywhere. So if you want to relate two tables, right, please make sure that you're using your referential integrity keys there. You're using primary key, foreign key combinations. If you take care of these two elements, your 1NF, 2NF, 3NF, most of these will resolve themselves. Now this I'm talking about in terms of when you actually implement normalization into a database. All right, so please remember these 2 points very, very carefully. First, logically club together only those records that you feel will logically be part of one particular entity. And secondly, after you've done that, if you want to club two entities together, make sure that you've got your referential integrity. I'm sorry about that. You've got your referential integrity in place. So use primary key, use foreign key for linking various relations together. And please ensure that in each and every table, you have a primary key. Try to avoid weak entities as far as possible. All right, I'm saying avoid weak entities. You can't completely eliminate them, but as far as possible, avoid them. All right, if you take care of these three basic pointers, all of your normalization forms should sort themselves out at the end of the table, right? So I really hope all of you have gained at least something from this particular session. I would really like your feedback, so please put your feedbacks onto the chat here. Please make sure that you're actually putting up your doubts too, so that any succeeding sessions can take care of those doubts. And I hope everyone stays safe. I hope everyone keeps social distancing, and hope everyone is safe and their families are safe. So that's it for this particular session. Thank you so much all for joining this particular session.